Hey everyone. While the homework solutions have been sent out and you can easily see what you did correctly or incorrectly, most of you did totally fine on that assignment. It was pretty straightforward. Just wanted to discuss a couple things about energy for our simple harmonic oscillators. So we focused for the pendulum on kinetic energy and gravitational potential energy. Kinetic energy, as you know, is 1/2 mv squared. So it's really about the velocity. Where is the velocity the greatest? Where is it the least? So at the top here, the velocity equals 0. So that means the kinetic energy has to be 0 because the pendulum comes to a stop. Same thing on the other side here. Velocity equals 0, so our kinetic energy must also be 0. But at the bottom, that's where the velocity is a maximum. And therefore, the kinetic energy must be a maximum. In terms of gravitational potential energy, gravitational potential energy is mgh, mass times gravity times height. So it's all about height. And at the bottom of our swing here, that's where your height is the least. Its height is 0. So therefore, gravitational potential energy is 0. At the tops, though, the height is a maximum at the top of the swing. So your potential energy due to gravity is also a maximum. Same thing on the other side. Most of you did okay with that. It was the mass on the spring that was a little different. Now, same thing. Kinetic energy is 1/2 mv squared. And again, it's all about velocity. At the top and the bottom of our oscillation, the velocity is 0. Therefore, your kinetic energy must be 0. The thing has come to a stop. Spring potential energy is all about distance from equilibrium, 1/2 kx squared. So x is distance from equilibrium. That's this green, now greenish black dotted line running through the middle. In the middle, you are at equilibrium. So your x, your displacement from there, is 0. So your spring energy is 0. At the top and the bottom of the oscillation, the x is a maximum. Your distance from equilibrium is a max. Not going to get any farther than that. So your spring energy is also a maximum. So I just want to address that with you all because we could, and we usually do, connect a little bit more with energy to our new expressions with, for simple harmonic motion, the t equals 2 pi square root stuff. We usually actually connect back to our unit on energy, but this time we're going to keep it pretty straightforward and just conceptually discuss where energy is the max and a min and related to the equations for each type of energy. So now what we're going to do is we are going to move on and discuss simple characteristics of waves. So let's say, for example, that you notice there is a leaf floating in some water, like at a pond or something like that, and you throw a rock a couple feet away from that leaf, and hopefully in your mind you're seeing these cylindrical waves rippling out from where the rock hit the water. And then you could see this leaf or bug or whatever it is probably going up and down on these waves. And if we were to graph its position as a function of time, I think you could probably guess what it would look like. Or maybe if you think about the mass on the spring moving up and down, and if you graphed its vertical position as a function of time, or even the pendulum as a function of time, are you seeing the signs that I'm trying to paint for you? Pun intended. So hopefully what you're seeing, a very crude graph, would be something like this. Get it? Sines. Sorry, that was pretty horrible. Or actually, that's cosine, isn't it? My bad. Either way, this is a wave. It's basically a wave function. Hopefully you've seen this before, and some of you have seen this before in your math classes. You've done things like this. That's fine. We do need to make sure you have the basics when it comes to the waves. So couple things. These high points here, these are called crests. And the low points are called troughs. Just bringing that to your attention in case you didn't know, because a problem may mention the distance between crest and trough is blah, blah, blah. So one full wave is wherever the wave starts to repeat itself. So we could say that from here to here, where it passes through equilibrium, that's a full wave. Or we could say it's from crest to crest. That's a full wave, or maybe even trough to trough, or wherever the wave starts to repeat itself, from this equilibrium to this equilibrium. Those are all one full wave. So rather than make this more confusing, let's just focus on one full wave. There's one full wave. You could actually divide the wave up into 4 parts if you wanted, from equilibrium to crest, from crest back to equilibrium, equilibrium to trough, and trough back to equilibrium. Any of these one sections is a quarter wave. So this section here is a quarter of a wave. The next section is a quarter wave. So basically, anytime the wave goes from equilibrium to crest, or equilibrium to trough, or vice versa, you're talking about a quarter wave. So any of these things here is simply 1/4 of a wavelength. I break it up into quarters because that's all we're really going to do. So we either have quarter waves, or half waves, or 3/4 waves, or full waves. And you just simply need to recognize is that anytime it goes from your equilibrium line to a crest or a trough, that's a quarter wave, excuse me. And if it goes the other way, it's a quarter wave. Or you could do equilibrium to equilibrium. That would be a half a wave. From here to here, that's 1/2 of a wave. Or from crest to trough, that's another half wave, because from crest to trough, I'm adding 2/4 to get a half wave. For some of you, you're like, why are you explaining this overly? We get it. I understand, but there's always some people that are having a little difficulty understanding what a full wave looks like, and that's going to be important later when we talk about musical instruments. So let's get into a little bit more of the mathematics of this, which are really straightforward, as well as the being able to read a graph and extract information from it. We just looked at what a graph of the amplitude of the oscillation versus time would look like. So I'm just going to draw that again here. It doesn't always have to start cosine-ish. You could start at sine-ish or wherever you want, but that's where I guess I'm most comfortable drawing. Now, that's the amplitude of the ripples as a function of time. But what if you could take a picture, go back to that rock being thrown in the water, and you take a snapshot of all those ripples going out? And if we graphed the amplitude versus position in the lake, you actually get the same thing. So these graphs look very much alike, except that one of them is versus position, hence the meters, and one of them is versus time. Be aware of that when you're looking at some of the examples. A couple other things to keep in mind. On the side here, this is the amplitude of the wave, either from equilibrium to trough or equilibrium to crest. The height of the wave, so in this case, the amplitude would be 3 meters. Yeah, that should be meters, sorry. And the height of the wave would simply be the entire thing. Not that we talk about that much, but that would be a 6-meter high wave, or 6 centimeter, whatever this is for this example. So we have to define wavelength. Wavelength is the length of one full wave. And we've already said that could be equilibrium to equilibrium, crest to crest, trough to trough, or the other equilibrium to the other equilibrium. Not my best birdie bracket there, sorry. The symbol for wavelength is lambda. It's like upside down Y, or it almost looks like a gimel, if you know what I'm talking about, my peoples. So lambda is wavelength. And it's measured in meters, as always. Okay, so wherever the wave starts to repeat itself, if you did something like, oh, I don't know, I'm just going to say from this equilibrium position, that's a half a wavelength. All right, that's why we went over the quarter, half, three-quarter, full wave on the previous page. On the other graph, wherever the wave starts to repeat itself, again, is one full wave, the time it takes to make one full oscillation. So that could be equilibrium to equilibrium, crest to crest, trough to trough, wherever the wave starts to repeat itself. This is T. T is the period. We've seen this before when we did circular motion. So T stands for period, measured in seconds. It is the time for one full oscillation. One full oscillation. It's literally seconds per oscillation. You may see it as seconds per revolution, but either way, seconds should be in the numerator. I throw that out there as a hint, something else. But we also have to define frequency. Frequency is lowercase f, and it's measured in hertz, Hz. And it's the number of oscillations or revolutions per second. Oscillations per second. So that's kind of like either oscillations per second or revolutions per second, but either way, it's per second. That's what hertz means, 1/seconds per second. Hopefully, you're looking at these two and you're seeing something special about period and frequency, especially if one is seconds per revolution, the other is revolutions per second, or oscillations per second and seconds per oscillation. Don't overthink this one. The frequency is the inverse of the period. I wouldn't necessarily call this an equation so much as just a concept. Some people, for whatever reason, really have difficulty separating these two. There's always a few. I'm sorry if that's you. Period is time, seconds. So if you're given a problem that mentions something like, oh, I don't know, let's make this up. There's 10 oscillations in 20 seconds. Some people are just comfortable doing the period. If you're going to do period, put seconds in the numerator. So I would have 20 seconds over 10 oscillations gives me a period of 2 seconds. Other people like frequency better. And if it's frequency, seconds goes in the denominator, right? Oscillations in the numerator. 10/20 equals 0.5 hertz. Look, they're inverse of each other. For some of you, you're saying, why is he going over this? This is not a big deal, but I swear there's always a few people that have difficulty with the difference between period and frequency. If this is you, just choose one of them and go with it. I don't know, whatever's better for you. All right, but back to the math. Okay. One thing we should know about these waves. For now, the velocity of a wave is constant. That's pretty important. That means we can use our old friend, very old, talking back in September, V equals delta D over delta T for the distance traveled or the velocity of a something moving at a constant speed, in this case, a wave. Now, what we could do is look at this a little bit further, and we're not going to think about this, but the units are meters per second. Please don't think about this too difficultly. We want to come up with a new expression specifically for the velocity of a wave. Now, the wave is still moving at a constant velocity. So if we want to know how far the wave travels in 10 seconds and we know its speed, we're still going to use V equals delta D over delta T. But if we want to figure out the velocity of the wave itself, we need a new equation. So don't overthink this. The units are meters and seconds, meters per second. Do you think you could put any of the new terms like wavelength, period, or frequency together to get velocity and get units of meters per second? You can pause the video if you need to. You shouldn't need to, though. If it's meters per second, then the velocity of a wave, meters, seconds, is lambda wavelength divided by period. It could also be, since frequency is 1 over period, velocity equals f lambda. Some of you may have seen that in chemistry. I'm not sure. These two expressions are actually identical. It's just one is using frequency, one is using period. But I want to stress to you, these two here on the bottom, these are used to get the velocity of the wave. We can still use the v equals delta d over delta t like we used to. So if we figure out the velocity of the wave is 5 meters per second and we want to know how far it travels in 2 seconds, we're going to use our old friend for v equals delta d over delta t. This is about linear distance traveled. So other than that, the homework associated with this is really straightforward. You're just asked to apply the new math and be able to read the graphs. I just want you to know that in class, we never did an actual example. We only did what you see here. We have a blank graph of amplitude versus position, amplitude versus time, and you were given the homework and expected to figure out everything you could just by looking at a graph. And you'll be fine. If you're not, you can email me or stop in for office hours. I have to tell you one more thing, and I'm out of screen space, so if you want to pause it, now's a good time. Sometimes a problem will mention echoes. How long does it take to hear the echo? So as an example, here's you. And you shout. And you're like, oops, you have a mouth in the center of your head. We'll just make you smiling. And there's a wall over here. So when you shout, the sound wave travels toward the wall. It hits the wall and bounces back, and you hear it. Let's say that this takes 10 seconds to hear an echo. That means that the whole trip there and back was 10 seconds. Please don't overthink this. If the speed of this wave is constant, how long does it take for the wave to go from the person to the wall or the wall back to the person? Yeah, 5 seconds each way. Just want you to be aware of that. That might come in handy. Other than that, if you need any help with anything, please do not hesitate to email me. I'd rather you turn in correct work with a good understanding and use me as a resource rather than rushing to get something done and doing poorly on it. So stop by for office hours if you need me, or just simply send an email with your question and often a picture of your work, and I'd be happy to help you. Thanks, you guys. Hope you're all doing all right.